Hello and welcome to today's lesson on a force on a charged particle, which is part of the magnetic fields topic in AQA A-Level Physics. So in today's lesson we're going to look at the magnetic force on charged particles. So we should be able to calculate the force on charged particles moving in a magnetic field. So if we've been successful and learnt in this lesson, we should be able to calculate the magnetic force on charged particles moving in a magnetic field, detail the direction of the magnetic force on positive and negatively charged particles, and calculate the magnitude of the magnetic force produced in the circular path of particles in various applications, which falls into the following part of the AQA A-Level Physics specification 3.7.5.2 moving charges in a magnetic field. So in previous lessons we considered placing a current carrying wire in an external magnetic field. So as a result, the difference in the magnetic flux density on either side of a conductor produces a force on the conductor, which is called the magnetic force, which is given the equation F equals BIL sine theta. Now it's important to note that in today's lesson we're going to look at the force placed upon a charged particle in a magnetic field, a microscopic quantity. So when we consider the force placed on a charged particle when it's in a magnetic field, that a charged particle moves, such as when it's in a current, it'll produce its own magnetic field. So as a result, when placed inside another magnetic field, the two fields will interact and this produces a resultant force on the charged particle. Now we observe this macroscopic force as the force on a wire because it's an accumulative effect of the force on all the charged particles. However, we can work out the force exerted on each individual particle inside of a current carrying conductor. So we can manipulate the equation showing the magnetic force acting on a wire or conductor in a magnetic field into the equation showing the magnetic force acting on a charged particle in a magnetic field. So let's start off with the equation we've looked at previously. The magnetic force equals B times by I times by L. Well, we know that I is equal to the change in charge divided by the change in time. That's the definition of current. So therefore B times by Q over T times by L. Therefore, we also know that length is equal to velocity times by time from our equation speed equals distance over time, or velocity equals distance over time. So we know that B times by Q over T times by V times by T. So the T values in that equation cancel through, so we get the magnetic force equaling B times by Q times by V. So this means that this is the equation for the force exerted on one particle. So let's consider a charged particle such as an electron placed in a magnetic field. Now we'll assume the current flow in this situation, the electron flow, is from left to right. Now it's important to note that the current is caused by also having an electrical field present, a plus and a minus. Now the electrical field acts in one plane and the magnetic field acts in a perpendicular plane to the electrical field. So for example, the south and north pole are in the vertical plane and the positive and negative of the electrical field are in the horizontal plane. Now this 3D concept cannot be easily shown on a 2D screen. You'll have to visualize this in your head. Now the current has been drawn in due to the electrical field, but to simplify the diagram we're going to remove the electrical field notation in the following animations, but it's still going to be present. Now in this situation we are aware that the magnetic force acting on the charged particle is acting out of the page. This is derived from Fleming's left-hand rule. So the electrical force acts in the direction of current flow, and we've looked at this previously, but the magnetic force and the electrical force are perpendicular to each other. So the electrical field and the magnetic field are always acting at right angles to each other. Now remember, the path of this charged object would not actually be parabolic because there's a resultant force in the vertical, which we're going to assume is the magnetic field in this example, and a resultant force in the horizontal from the electrical field in this example. So there's no inertia in either plane, so you wouldn't get a parabolic path. But we can work out the magnitude of the magnetic force exerted on a charged particle due to being inside a magnetic field with the following equation. Magnetic force is equal to B times by Q times by V, where F is the magnetic force in newtons, B is the magnetic flux density in Tesla, Q is the charge of the particles in coulombs, and V is the velocity of the particles in meters per second. Now the most common charged particle which moves in a magnetic field is the electron, so this makes the charge E. So we can write the equations F equals BeV. So the force makes the charged particle deflect to the oppositely charged pole, i.e. the negative charge would go to the north pole and the positive charge would go to the south pole. Now this equation is sometimes known as the Bev equation because it's the Bill equation but for one particle only. So if the charged particle is not moving, then it doesn't produce a magnetic field, which means it would not interact with the external magnetic field. So this is demonstrated in the equation, because if V in the equation is equal to 0, then F is equal to 0, which means that the particle would not move towards the North Pole. This makes sense as the particle is not moving. It's an important idea to note that the magnetic force is only ever exerted if the particle, which is charged, is also moving. Now again, this equation will only work if the magnetic field is acting at right angles to the velocity of the particle, so the magnetic force is acting as a centripetal force, and this is shown in the left hand rule, like we mentioned before, that the magnetic force always acts at right angles to the velocity of the particle. But if they weren't at right angles to each other, the equation would need to be amended to say F equals BQV sine theta. So from the left hand rule we can determine the direction of the force acting on charged particles in the magnetic field. So the direction of the force in this example is acting out of the board or out of the screen. So if we take an overview of the charged particle movement, we can see the magnetic force is acting in one direction and the current flow is perpendicular. So it's important to note that the magnetic force acts perpendicular to the direction of current flow. So this means that the magnetic field accelerates the charged particle via deflection. The electrical field would accelerate the charged particle by changing its speed, as it's in the same direction as the movement of the particle. So the correct directions of the force are not shown in this diagram, as the circular path will be a 3D effect, but what you can see is that the magnetic force always acts perpendicular to the motion due to the left hand rule. So if the magnetic force is always acting perpendicular to the motion, it causes the object to rotate in a circle. So the magnetic force acts as a centripetal force, as you can see in this particular animation as shown. So if we can say that the centripetal force equals the magnetic force, well, we know that the centripetal force is equal to BQV. So mv squared over r, which is the centripetal force, equals bqv. So as a result we can cancel out two of the v's, one on either side of the equation, so therefore we can say r is equal to mv over bq. So it's important to note that if the magnetic force acts as a centripetal force, we can derive the following equation. The radius of deflection, the amount of the size of the circle that the particle will make out in its path, will be equal to m times by v over b times by q. So it shows that there are four factors which affect the velocity of a charged particle in a magnetic field: the mass of the particle, the radius of deflection, the magnetic flux density of the magnetic field, and the charge of the particle. Now, important to note in this situation that in both of these examples we can actually band the mass and the charge of the particle together as the specific charge, which is just the charge to mass ratio of the actual particle. So we can use this equation to determine how changing a factor would change the radius of the deflection. Now it's important to know that this equation is not given to you in an examination. It's a marking point to remember that the magnetic force acts as a centripetal force for a charged particle. So it's an important idea to note that if you wanted to maintain the radius of the charged particle's motion, you would need to keep the speed, the magnetic flux density in proportion to each other, as you can't affect the specific charge of a particle to maintain that radius. So you can also state the idea that if you increase the velocity or speed of the particle, the radius of deflection will be bigger, whilst if you increase the magnetic flux density of the magnetic field the charged particle is in, you will decrease the radius of deflection. So what have we learned in today's lesson? Forces on charged particles moving in a magnetic field are given with the equation F equals BQV when the field is perpendicular to velocity. We should be able to work out the direction of force on positive and negatively charged particles and understand the circular path of particles and the applications in devices such as a cyclotron. So if we're being successful and we've learned in today's lesson, we can calculate the magnetic force on charged particles moving in a magnetic field, detail the direction of the magnetic force on positive and negative charged particles, and calculate the magnitude of the magnetic force produced in the circular path of particles in applications. I hope you've enjoyed today's lesson where we've looked at the force on a charged particle in a magnetic field, which is part of the magnetic fields topic in AQA A-Level Physics. Thank you very much for listening to today's lesson and have a lovely day.